last topic pretty much of the syllabus that would be on the final exams. I, of course, won't ask you too many detailed calculations for three-dimensional problems, either trusses or frames, but that's sort of the last topic that's left. And then next week, as I mentioned, Dr. Liu will give you sort of a primer on SAT 2000, what are some of the basic capabilities and some intermediate to advanced capabilities, what kinds of problems you can solve with it. And then I'll post a sample final exam. And I think on Friday she plans to do a review. I'll be there, of course, next week as well. But let her take the lead on those items. Any particular questions on? I think the main thing that we discussed about last time was how to do the shear force, axial force, and bending moment diagram calculations. If you have the solution for let's say a two-dimensional frame, maybe that example again. If we have this frame or any other frame with any type of loading, some boundary conditions, how do you go about solving it? And then so very quickly you build up the element stiffness matrices that was this big 6x6, as we found out in the local coordinate system. You need to take that 6x6, transform it from the local coordinate system to the global coordinate system. And by the way, the handout that I gave you probably did not have these details, but these details are all posted online on Blackboard. So make sure you download the latest PDF from Blackboard. So you transform the local coordinate system to the global coordinate system. That gives you a slightly modified 6x6. You do that for all the elements, and you assemble that into a big stiffness matrix, just like we did for trusses. And then you allow MATLAB to solve, and you get the solution at all the degrees of freedom, solution for displacements and rotations. This is the 15 degrees of freedom, global degrees of freedom for this problem. And this is the 15 degrees of freedom for the forces and the reactions. So the question is, if I have this solution from MATLAB, how do I plot the axial force, shear force, and bending moment diagrams? What do I need to do first? Let's say for element 1. Spencer? The global or the local? And actually, say for example, if you want to find the axial force, shear force, bending moment for element 1 here, what you would do is to pick out those degrees of freedom from here, which would be 1, 2, 3, 4, 5, 6. So the first 6 degrees of freedom right here. You pick those out, and as I was showing you last time, you get those 6 degrees of freedom. Those are in global coordinates. So I need to first convert them to local coordinate system by doing the inverse transformation, like we to go from the global to the local, we do an inverse transformation that I showed you in the MATLAB code. And again, you can revisit the last video to make sure you understand the process. Once you have the local degrees of freedom, then you multiply it with the local element stiffness matrix. K element local is what you need. Multiplied with the degrees of freedom local to get local forces. Those local forces, as I pointed out last time, were Qi x prime y prime, Qj x prime y prime, and then Mi and Mj. And of these, Qix was the negative of the axial force, Qiy was positive shear force, Mi was negative bending moment, and these guys were positive axial force, negative shear force, and positive bending moment. So you take those 6 numbers and you basically draw these 1, 2, and 3 lines, one for axial force, one for shear force, one for bending moment, and you keep on doing that same process again for all the other elements until you have the until you have all the other shear force, bending moment, and axial force diagrams. So that's the process I went through in a fair bit of detail, I think, last time. So if you're still not clear on how to do that, make sure you watch that video, and also download the latest notes from last time. Any particular questions on this? No? Okay. So last time we had also started this topic on space trusses, which is basically saying that you have a truss in 3D. Lots of structures obviously are like that, and the problem here is to try to again transform local element stiffness matrices, which are basically local force and displacement relationships, in three-dimensional coordinates. We have to transform some arbitrary x prime, y prime, z prime to another global x, y, z. And this local axis could be pointing in any general direction. For our two-dimensional problems, it was much easier because z prime was always oriented along the global z. So x, if you have x, y, it was always oriented along, it was always the mapping between these two coordinate systems was always in one plane. But now it's a three-dimensional problem, and it's much more tedious to do with trigonometry in 3 dimensions. So last time I was showing you a process by which you can very easily convert a system or components of a vector from one coordinate system to another. So let me repeat that. Say you have some vector, which could be a displacement vector, or it could be a force vector in some random direction in 3D. I can express the same vector in two different coordinate systems. I would get three components in, say, one coordinate system, which belongs to the global XYZ. I would get three different components in a different coordinate system, x prime, y prime, z prime. But since this is the same vector, I can express that vector in either of these coordinates. So if I want to relate, let's say, v1 prime to v1, v2, v3, or if I want to find the relationship between these two sets of components, here's the logic that we are going to use. We're going to say, I'll take that vector v, and I'll take a dot product of that vector v with e1 prime. So this is again a question I asked last time. What would I get if I take a dot product of v with e1 prime? What do we get when I take the dot product of any vector in some unit vector direction? A scalar component along that direction, right? So for example, here, I would just get v1 prime. If I take the vector v, if I take a dot product here, I would get v1 prime. A dot product with e2, I would get v2 prime. Similarly, v3 and e3 prime. So I'll express this logic, v dot product with e1 prime, as this entire thing, which hopefully you all can see is nothing but the expression of vector v. This is just taking these three components, multiplying them by their unit vectors, v1 e1 plus v2 e2 plus v3 e3 prime, dot product with e1 prime. Now e3 prime dot with e1 prime, what is that? 0, because the angle between e3 prime and e1 prime is 90 degrees, right? So that dot product is 0. Similarly, e2 with e1 is 0. So those two terms vanish, and what I'm left with is v1 prime times e1 prime dot with e1 prime. Of course, e1 dot with e1 prime, or e1 prime dot with e1 prime, is 1. I'm just taking dot product of a vector, unit vector with itself. That allows me to write on the left side this component v1 prime, and on the right hand side I'll take the same vector v. This entire thing, hopefully you can again see, is vector v in a different coordinate system, dot product with the same e1 prime that I wanted. So on the left hand side and the right hand side I have the same quantities, but on the right hand side, e1 dot with e1 prime is not going to be 0 or 1. It's going to be what? What is e1 dot product with e1 prime? how could I mean, physically, it's taking one unit vector, another unit vector pointing in a slightly different direction, and then I'm taking a dot product of those two vectors. When I take dot product of any two vectors, A and B, for example, what I get is magnitude of A, magnitude of B, and cosine theta, right? That's the dot product, where theta is the angle between them. So if I have two unit vectors, the magnitude of both of those unit vectors is 1, and what I get is cosine of the theta, the angle, the three-dimensional angle between E1 prime and E2, E1 prime and E1. That's what I get for E1 prime dot with E1. And I'm going to call that Q11. Similarly, if I take the second component, I get E1 prime with E2. I'm going to call that Q12. That's cosine of the angle between E1 prime and E2. Similarly, E1 prime, E3, that's Q13. And if I repeat that process by taking dot products with E2 prime and E3 prime, I get these three different equations. So I have these three equations which now relate. Now I have a relationship between V1 prime, V2 prime, V3 prime, and V1, V2, and V3. V1, V2, and V3 in all three equations. Right? So this equation, of course, or these three equations can be represented very compactly and nicely in a matrix form, where again we have something like a local components times a transformation matrix transpose and the global components. This relationship is the three-dimensional equivalent of the two-dimensional relationship that we had derived long back, which was this guy, right? In 2 dimensions, you remember we said local components are given by transformation matrix transpose times the global components. That's exactly the two-dimensional analog of the relationship that I'm talking about. So this sort of complicated but very easy, very systematically derived relationship that can be easily coded up in a computer. That's the same relationship, but now in 3D. And in quite a lot of other places, you'll find very complicated geometric, trigonometric formulas to convert from one arbitrary three-dimensional coordinate system to another. All that's not quite necessary. You can use this logic to derive that very, very easily. The other thing I pointed out was that the element local stiffness matrix still remains exactly the same, except that's now bigger in size. That relationship, even in 3D, is that a truss element can be either in tension or in compression, where that force in tension or compression is exactly dependent upon the change in length. So as long as I can find out what the change in length is, I can relate forces to displacements for a three-dimensional truss element. And again, as I pointed out last time, the change in length is decided only by displacements in the x prime direction in the local coordinate system at nodes I and j. Y prime, z prime do not matter, and therefore what we get is the same 1, 1, minus 1 of the off diagonals. Everything else is 0, because this maybe I'll just write that here: x prime, y prime, z prime, x prime, y prime, z prime for the two nodes, and the same degrees of freedom on the in the rows direction, and we get that is the stiffness matrix. To convert that local stiffness matrix to global so that we can actually assemble them, if I have lots of truss elements, in 3D all pointing in all different directions, I have to convert all of them to a global coordinate system first before I can add them or I can assemble them. So that assembly procedure is exactly the same as we had in 2D. You remember we had transformation times local stiffness matrix times transformation transpose. So the only thing that has changed now is that the size of these matrices is 1 bigger. And what we get is a 6x6 global 6x6 element stiffness matrix in the global coordinates. And at that point, we already know we have to assemble all of them together. We get a big, huge global system matrix, divide it into free and specified degrees of freedom, and solve. So let me show you this example code that we had just sort of started talking about. So for this problem, we had these 4 nodes at the base, 4 nodes at the top, and the main difference in the input file here is that, of course, that we have a z coordinate along with the xy that we had before, but now the element description is a little more complicated. So if node 1 is connected to node 5, the last 2 entries are Young's modulus and area of cross section. For simplicity, I've just let them be 1 here. But there are these 3 numbers in the middle which represent E2 x component, E2 y component, and E2 z component. And last time I was telling you that if, for example, if you have a truss element oriented in some direction, then the direction along the element, if this is node I, this is node J, we know that the direction along the element we can calculate just by, sorry, I should call it NM. This is element M, so this is NM hat. We can find this direction purely from the nodal descriptions, but we do need what is the y prime direction and the z prime direction. So there is some ambiguity about in which direction is a truss element oriented in 3D. So if I have a member that does not, for truss problems, it's not that big of a problem, but for frame problems, it definitely is. That you need to define in which direction is your major axis and minor axis oriented. So just to give, or just to find a direction, let's say perpendicular to the element, that would be one direction, M, or let me call it exactly what I have it here, E2 hat. This E2 hat direction is perpendicular to this beam or this truss element. And if I can specify this as the direction of the major axis, then the third axis, which would be the E3 hat, that can be obtained by simply taking the cross product. E3 hat is equal to NM hat cross with E2 hat. So these 3 numbers are generated by randomly by finding a vector that is perpendicular to this truss element. And last time, if you remember, I said that you take any random vector v to generate E2 hat. The way I generated E2 hat was you take any random vector v, take a cross product of that vector with the NM hat vector. What do I get? What would I get? So let's say this is my truss element. It's oriented in some random 3-dimensional direction. I take another random vector v, and I take a cross product of that vector with this truss vector. What would I get? A vector that is perpendicular to this truss element, right? So if I take a cross product, I get a vector perpendicular to the truss element. And what do would that be a unit vector? In general, not, right? So in order to convert it to be a unit vector, I'll just divide that by the magnitude of the same thing. Take the vector v, cross product with, sorry, NM hat, and now I have a unit vector that is perpendicular to that truss element, and that's what this unit vector is. So generating even the input file for 3-dimensional trusses is a little more complicated than what we had in 2 dimensions. Okay, but essentially that's what these middle 3 numbers are. The rest of it is exactly the same way. Boundary conditions on nodes 1, 2, 3, 4, that x, y, and z components are all 0. Nodal loads 5, 6, and 7, and 8. I have some nodal loads in the x, y, and z directions, which is what is given here. And then finally, I have, maybe I'll pull up the code here. Let's see if I can. Truss3d.m. The structure overall is exactly the same. The main difference really is that the element degrees of freedom are now from 3i minus 3i minus 2 actually. So this minus 1 times 3 plus 1 will become 3i minus 2 to 3i, and um, assembly is exactly the same way, solution is exactly in the same way, the same exact two lines, and after that it's all just plotting. So maybe let me run that. I have a truss 3D, one of those truss 3Ds problems, and this is the example in the handout that you have. Um, of course, very complicated to look at in 3D, but um, I think it's more important to understand exactly how this solution was computed. Maybe I'll give you another example. I don't myself remember what the other input file was. Let's see. It was 3D2. Huh. Yeah, so this example was the example from your homework maybe a while back that you did with the method of joints, right? Um, so um, so essentially, yeah, that's how you would generate input files for three-dimensional trusses. And of course, I'll post this code also online. So if you need to use it, you can. Any questions um, on this truss topic? All right, so let's take a look at three-dimensional frames now. Um, and of course, these are most building structures that we see around us. This building we are sitting right now is a three-dimensional frame structure. And the idea, of course, is that each of those elements can behave in both an axial and a bending manner. So how do we solve or how do we simulate these types of structures? Um, the the ideas again are very simple as with our two-dimensional frames, but now there are additional complications because you have 3 degrees of translation at each node. Those are my W1, W2, W3. Those are for any particular element. For example, if I take this element right here, um, at 2 nodes, it has W1, W2, W3, 3 translation degrees of freedom and 3 rotational degrees of freedom. Now, in 3 dimensions, if you have rotations that are not negligible, if they have moderately large rotations, then they are all coupled to each other. And then they are not independent the way that most structural analysis softwares would treat. But again, if deformations and rotations are small, then you can say that all of these 3 rotations are independent. And similarly, at the other node, you have 6 degrees of freedom. So now you have an element which has a total of 12 degrees of freedom, 6 at each node, 3 translations, 3 rotations. So it becomes a bit of a fairly cumbersome job to try to figure out how are all the forces and moments related to all the displacement and rotation degrees of freedom. So here's an example. I have this frame element. Let's first of all constrain ourselves to be along its local coordinate system. So if the frame element is pointing in some general three-dimensional direction, I'm going to view it in its local coordinate system. And just to make it simpler to see, I'll put it like this. So the deformations that it has, one of the deformations is axial. Okay, the simplest one is axial. So the axial response is once again exactly the same way that a truss element would respond. If I have node I, node J, I can find the displacement in the x prime directions at J and I, and I can relate them with exactly the same stiffness matrix AE over L, and one's on the diagonals, -1 on the off diagonals. Which degrees of freedom does this relate? W3 and W3 from between 1 and 2. Those are the only 2 degrees of freedom that it's relating. Okay. So that's one part of the response. Another interesting and new part of the response is now in torsion. So if I take this frame element and if I hold on to the left or the back end and take the right end and rotate it, that's twisting. Okay, so if I twist it, and according to my right hand thumb rule, that points out in this direction, also in the W3 direction, right? So that's this direction. That's relating the rotations between 1 and 2 in the 3 in the axial direction. So that's a uh, uh, new relationship that relates moments at the two ends with the rotations theta at the two ends. So that's G, J over L times a very similar matrix that we had for the axial. Anybody remember what J is? Polar moment of inertia, right? And G was the shear modulus. Um, so, right. So those are the axial and the torsion components. And in addition to that, we will have 2 bending components. One for, if I have this as a frame element, one for bending in this direction, and another for bending in the out of plane direction like this. Make sense? So, of course, if you're bending in this direction, if you're bending in this direction, that's bending in the minor axis. If you're bending in this direction, that's bending in the major axis. For non-rectangular or non-square or non-circular cross sections, the second moment of area about um, let's say the x2 axis or the x1 axis would be different, and that's what we have here. But the response would be only governed by this IY or IX. Everything else remains exactly the same. This first matrix, this first 4x4 matrix, which hopefully you recognize is the same matrix that we had for beam elements, correlates not 1 and 2. W1 and theta 2. Does that make sense? W1, that's the transverse displacement in the one direction, and transverse displacement in the one direction will have rotation in the theta 2 direction. Let's check that. If I have beam bending like in this direction, then I have displacement in the vertical direction at some point, and the rotations are pointing out of the plane. So if my displacements are in the W1 direction, my rotations would be clockwise or counterclockwise pointing out or into the plane. So that's why W1 and theta 2 are linked for both nodes 1 and 2, and W2 and theta 1 are linked right here. W2 and theta 1 are linked for both nodes 1 and 2. So that's the other thing. The first one I showed you was W1 and theta 2. The other one would be in this direction. That's W2 pointing out, and if I'm taking rotations like this, then that would be theta in the one direction. And that's again a 4x4, exactly the same structure as this bending, but with a different second moment of area. Now we have all of these components that completely define how will all of these degrees of freedom interact with each other. But the key assumption that we have made is that bending in this plane does not affect bending in this plane, which is also a valid assumption for very small, for small deformations. Okay? If your deformations become large, if your beam is already bent like this, and now you try to bend it in this way, you will get a different behavior. So for small deformations like we have in our civil engineering structures, this is a valid assumption to make, that all these 4 modes of deformation are decoupled from each other. They do not depend upon each other. So now the trick becomes, now that I have these four different modes of deformation, how do I combine them all to put them all in a big force element relationship that should really be 12 cross 12, right? I have 12 degrees of freedom in total. I have 12 forces and moments. So I better be able to relate all of those with each other, which is what is given on the next page of your handout. Um, and all that it is, this is a big 12 cross 12 stiffness matrix that is relating the degrees of freedom, the 12 degrees of freedom for that element. If you take that K, this stiffness times this degrees of freedom, you get those 12 forces and moments. And how did I construct this? We should be, or you should be able to see that the structure of this matrix is EA and this 1 over L cube outside. So EA over L minus EA over L minus EA over L plus EA over L. That is corresponding to degrees of freedom 3. That's along the axis. So that's the axial components, both in the rows and the columns. Okay. The slightly dark green terms here, they are for bending in the x2 x3 plane. Those are these terms. So they are relating w2 theta 1 terms. And lastly, the brown terms in there are for w1 and theta 2. So all that we have done is we've taken our beam element matrix, that 4 cross 4, and put them in the right location to relate w2 and w2 and theta 1 with so this is w2 and theta 1 between nodes 1 and 2, and similarly the brown terms are w1 and theta 2 for again for nodes 1 and 2. Everything else in that matrix is 0, but essentially that's the same type of process that we did when we were assembling the uh, frame element, right? We had an axial part and a bending part that I had already included, and then we added the axial part in the correct location. So that's exactly what we did for this frame problem as well. But now, as I said, it's a much bigger matrix. And finally, we have these torsional elements also. These torsional elements are relating theta 3. That's the rotation along the axis, or the torsional degree of freedom at both of those nodes. So Gj over L plus 1 and minus 1 on the diagonals exactly the same way. And now we have this big, huge 12 cross 12, which is sent into MATLAB's frame element routine. Here's a question. Do I need to transform this before assembling it for a structure something like this? How do I transform this? Indeed, I do need to transform all of that big 12 cross 12, 12 times 12, 144 different terms. They are all in the local coordinate system, right? So how would I convert that local coordinate system to a global coordinate system? By using the transformation matrix, which we have already derived for the space trusses. This transformation matrix, this is a 3 cross 3 transformation matrix that will take either displacements or rotations or forces or moments between some global components to its local components. So it's exactly this transformation matrix that we will use to convert the local degrees of freedom to a global degrees of freedom. Once I have converted it to a global degrees of freedom, then I can assemble them and I solve it exactly the same way that we did for all our previous problems. Here's, I think, maybe one discrepancy here. This matrix, I think, is actually a transpose. So this should really be here. think on the handouts, what you can do is put a transpose there, and then it would be okay. This matrix is the transpose of the matrix that I had defined for the space trusses. This guy. So you see Q11, Q12, Q13, and so on. And here, this matrix was used to go from, take the global components, multiply them with it to get local components. So for the frames, if I want to go to the other way, then I should have the transpose of that matrix, which is what I have Q11, Q12, and Q13. So I think, again, this is sort of an overview of three-dimensional trusses and frame type problems. Hopefully you see that the process with the stiffness method is the process is exactly the same. The details differ only in maybe the number of degrees of freedom per node that we have. Usually stiffness method doing by hand is extremely cumbersome, which hopefully you've realized with the homework problems or even the quiz 3 or quiz 4, which I actually need to return to you probably on Monday. Well, not probably, I'll return it to you on Monday. But the idea is that not to do stiffness method by hand. When you go out to work, whenever you graduate, you will not be solving structures by hand using any of the methods that you probably learned with 371 or 474. You would most likely be using some computer software which is running the stiffness method or possibly the flexibility method under the hood. It's far more important to understand that how those methods work, what can go wrong, and how do you correctly interpret the solution. Okay, so the difference between you and somebody who does not know structural analysis should be that you understand the solution that's coming out of the computer in a much deeper level. So I think this is also sort of a bit of a philosophical question. You learned all of these methods, right? Moment area method, slope deflection method, moment distribution method, flexibility force method, and virtual work method. Why did we learn all this when we are hardly ever going to use it when we graduate? We're just going to model it and run the results on the computer. Why did we even bother learning it? Any thoughts? Why did you learn all these methods of structural analysis? April?
So that you know what's happening in the program, so it's not just a black box, and also sometimes with some structures you just do it by hand, don't check people.
True. So you do, of course, need to understand what's happening inside the computer. But go ahead, Miles.
I don't know what be in this position that someone has to code the program, so
that's true. Yeah, someone has to code the program and someone has to expand its capabilities sooner or later. So you better know how that works. That's also true. But most engineers who go out into the real world would be doing some sort of a structural design and analysis. Do they need to go through all of these methods of structural analysis? What did that help you when you were going through all of these, learning all of these methods of structural analysis? In my view, the main benefit of doing all of that is that you learn to see behavior. You learn to see how a structure would behave. So you can solve the same simple problem, a simply supported beam uniformly distributed load, with any method you want. You are going to get exactly the same result. But the exercise of going through and solving it in 10 different ways, and actually there used to be a lot more methods in the past, but exercise of going through and solving it in 10 different ways gives you a lot more deeper insight, because each of those methods rely on certain properties of structural behavior. So you should learn to see structural behavior. What would happen if I apply the loads this way? The beam is going to behave this way, the column is going to bend that way, or it's going to sway this way or that way. That sort of insight is what I hope and what we hope that you have gained, and that may not be easily apparent to you. It's only when you start, you design structures every day after you graduate, then I hope you'll see the benefit of having gone through all of these different methods and their merit. So that's a little bit of a side of philosophy. I think in the last 10 minutes that I have, or 8 minutes that I have for the lecture today, I'll introduce um, related, but again, a topic that is not something that I've given you a homework problem or even a handout on. I'll post these notes and you can download them again. Um, this is a topic which deals with constraints. A lot of times our structures are constrained in some manner. One example of a constraint is an internal hinge. Any idea how you can solve a problem with an internal hinge? For a beam problem, let's say I have a cantilever beam with a roller support at one end, becomes indeterminate, so I immediately create an internal hinge. Now it becomes determinate. How would I solve this problem? Let's say a point load at the internal hinge. How would I solve this problem with, say, the stiffness method? With every other method, I'm sure you know how to do that. But I have not really talked about internal hinges with the stiffness method. Any thoughts on how you could solve that? If I didn't account for the internal hinge, I would just have two elements, right? Find the stiffness matrices of those two elements, assemble them together, solve it, and what I would get would be some displacement at the midpoint and some rotation, one rotation at the midpoint. But if there's an internal hinge, the rotation at the midpoint could be two different from between left and right. So how would you deal, any ideas how we can solve this? Problems with internal hinge? Okay, split it into two systems. So I have, let's say, maybe I'm just sort of going through this this slide as well. If you split it into two systems, what you're saying is essentially to create a duplicate node right here. So 1, 2, 3, 4. All right, so I have now two systems. And if I have these two systems, they are completely disconnected because element 1 goes from 1 to 2 and element 2 goes from 3 to 4. There's no connection between these two guys. So what additional connection do I need? Right, that the displacements at where I created the duplicate node have to be the same. And that is a perfect example of a constraint. So I have two structures essentially, and I'm saying that the displacement at one point of one structure is equal to the displacement of another point of another structure. That's an example of a constraint. I've tied those two nodes or those 2 points together for two different structures. So that's exactly what this diagram also shows. The way we'll do that is create a duplicate node here, which means that I'll have degree of freedom 3 from the left, degree of freedom 5 from the right, and two different rotations 4 and 6. I want to keep the two different rotations 4 and 6 because of the internal hinge, but I want to make sure that the displacement at 3 and 5 that I get from the two halves structures is the same. So the way we would do that is go about creating element stiffness matrices exactly the same way, assemble them in exactly the same way. After we assemble them, you'll see that what we get is for element 1 something like this, which is degrees of freedom 1, 2, 3, 4. Element 2 from 5, 6, 7, 8. So that's 5, 6, 7, 8. And finally element 3, which would be 7, 8, 9, 10, which clearly shows that that degrees of freedom 1 through 4 are pretty much disconnected from 5 to 10, right? This is, there's no connection between these two guys. And everything else, of course, on the off diagonals is 0. So what we do is we say that I want to make sure that displacement at 3 is the same as displacement at 5. That's the constraint. And the way we solve these types of problems is by actually working with a reduced set of degrees of freedom. Those reduced set of degrees of freedom are here on the right. I have D1, D2, which are fixed. D3, D4, I'm going to get rid of the degree of freedom 5 because that should be the same as D3. D6, D7, everything else remains the same. Now, if I'm going to get rid of this degree of freedom, the fifth degree of freedom, I need to get rid of the corresponding column of what is a transformation, what really is a transformation matrix. So hopefully you all see that this structure here is just an identity matrix. If I did not delete this row and this column, I would have identity matrix times a vector. Identity matrix times a vector is what? An identity matrix times a vector gives me back the same vector, right? If I delete that element 5 and I delete that column 5, because of course if you take that row multiplied by that column, then it's the fifth element in each row that gets deleted, which is the fifth column. So I'm saying that degree of freedom 5 here is the same as the third degree of freedom, which is why we have this 1 shifted over from the fifth column to the third column. And I'm going to call that a reduced transformation matrix that allows me to express the global degrees of freedom as some transformation matrix times a reduced set of degrees of freedom. Here's a question. For this particular problem, what is the size of this transformation matrix? 10 cross 10, or well, 10 cross 10 if it is, then I have not reduced anything, right? 10 cross 9. So 10 cross 9, because I still have all the 10 rows, but I've deleted one column. So 10 cross 9, of course, it's a rectangular transformation matrix. So this rectangular transformation matrix is not orthogonal. T times T transpose is not going to be identity. But we deal with this or we do this transformation in exactly the same way that we did for example, for the inclined support. If you remember, we'll pre-multiply by T transpose, the global system. I get T transpose times K global, and I'll express this dg as TR times dr. I get a new stiffness matrix K reduced and D reduced and F also reduced to a 9 cross 9 system, where I can easily calculate the third degree of freedom. I actually easily calculate all of these degrees of freedom, but in particular the third degree of freedom will be replicated to give me back the original degrees of freedom. So again, this is a topic that I don't expect you to do any homework or exam or anything on, but this is something to keep in mind, that with the stiffness method or with any method, sometimes there are things like internal hinges or other constraints that people have to work with. All right, so I'll stop at this point, and then next week, Dr. Liu will conduct some tutorial sessions on SAP, and finally a review for the final exam. Okay. All right, so I'll see you all on Monday next week. Thank you.